Right on. Okay, so good afternoon, everybody. The title of today's presentation is Gauge Digitizer Streaming Applications. I will actually be more focusing on the mechanics and architecture of streaming, but we will discuss streaming applications. So the talk is divided into three parts. I'll present our normal, conventional, traditional digitizer memory mode of operation, still the simplest way to operate the card, and if your application isn't too taxing, the way to go. And then we'll move on to discussing the more sophisticated and powerful streaming mode. And then finally, I'll end off with discussing some aspects of the throughput latency trade-off, which I'll describe. So we'll start out talking about our memory mode. So here's a picture of one of our gauge CompuScope digitizers. And the traditional way to work is to acquire a waveform into the card's onboard memory, which nowadays consists of 2 or more gigabytes worth of memory. So that's a lot. That corresponds to typically several seconds worth of acquisition at the top sampling rate. So you're able to acquire for, as I say, continuously for a few seconds until you fill up the memory. At that point, you had to stop the acquisition and then transfer the data to PC RAM where it could be used. While the data are captured into the card's onboard memory, it can't really be used the way data can to, manipulate an Excel or plot or whatever. For that, it has to be transferred to PC RAM. Now, during that transfer, we're blind. The card is unable to acquire waveforms while it's transferring data in memory mode. And that may be okay, depending upon the application. If you only wanted one waveform, one long waveform, no problem. You download it, you're done. Or you might have you might need to only capture, say, a microsecond or two's worth of data every millisecond. So you might be able to acquire the waveform's worth of few microsecond long waveform, download it in time before the next trigger comes a millisecond later. You're actually missing something like more than 99% of the data, but that's okay. You're only interested in a few microseconds worth after the trigger. Then you're fine in this case. But as I say, regardless of what, you're guaranteed to be missing data while you transfer the data from the card's onboard memory to PC RAM. The card can acquire in this mode in 2 separate modes: single record mode, where we just accept one trigger and acquire for as long as you want, up to, as I say, the several seconds of memory that are available on the card. Or you can use our multiple record mode. In multiple record mode, we're able to acquire multiple shorter waveforms and then stack them in the card's memory. So, for example, with, say, 1 billion samples of onboard memory, you could capture 1,000,000 point waveforms, which is a real case that can come up in a scan of 1 million different triggers, for example. But again, once you've filled up the memory with triggers, you have to stop and download all those triggers. So again, data loss is unavoidable, and that's an overview of our memory mode. Just to delve a little deeper into the single record versus multiple record case, if you had a repetitive waveform, you could capture it in single record mode, where you acquire, rearm the card from software, and then transfer the data, and then do that repetitively in a loop. You could do that all day. You could do that forever. Is the advantage of single record mode. The disadvantage, however, is twofold. First of all, you're doing the rearm of the card from software, which is always a little bit slower. And then second, you have to transfer the data. So you have to wait. In addition to the wait to acquire the waveform, you have to wait for this yellow part. Let me get my little laser pointer here. This yellow part here and this blue part corresponding to the transfer. You have to allow these 2 events to occur before you're ready for the next to acquire the next waveform. So that's the disadvantage. You're able to go at a very fast, repetitive rate trigger repetitive rate, PRF. This is the pulse repeat frequency. That's a little language borrowed from the radar world. So if you're so using single record mode for relatively short waveforms, we can typically acquire PRF, or trigger repetition rates, up to about 10 kilohertz without missing triggers. If you have faster triggers, then you might want to work in our multiple record mode, again, where we can stack the waveforms on the card. So here you acquire again in green, but then all you have to do is rearm, and the rearm's done in hardware very quickly, in under a microsecond. And then if you respect that 1 microsecond rearm time after the acquisition of the waveform, then you're ready to accept the next trigger. And you acquire rearm with no transfer in between to slow you down. And you can do that at rates of more than 100 kilohertz, 100,000 triggers per second. Of course, the downside of this method is once you've filled up the onboard memory, now you really have to pay the piper. You have to download all the waveforms, not just one, but all 1,000 or million of whatever you acquired. So sometimes I say to customers, it's like an installment plan versus paying it at once. You can pay your rent, every month, or you could imagine paying it all in one big lump sum at the end of the year, which I guess most landlords aren't usually amenable to. But in both cases, you'd pay the same amount. It's just in the first case, you're paying it spread out with monthly payments, whereas in the second case, you pay it in one big installment at the end of the year. So similarly, we can transfer the data after each waveform in acquisition in single record mode, or we can wait till the end, but we still have to pay about the same amount of transfer time. Okay, so the multiple record mode is good for burst applications, where you have a burst of triggers that occur, as I say, at very fast rates, but then you have a break afterwards to download the data. This can often happen in scanning in scanning applications, where you might have a million triggers that correspond to a scan. You could stack the entire scan up on the card's memory, but then after the scan's over, you can download the waveforms at your leisure. Just to dig in a little bit more to the single record mode, which is often the way people work if they want to go forever, as I say, without having to worry about filling up any memories or so forth, is to plot the maximum PRF, or the maximum trigger rate, as a function of the depth, which is the amount of samples we acquire per waveform. Okay, and we can see this shown for this Eon CompuScope card of ours in single and dual channel mode. Of course, when we work in dual channel mode, we can't go quite as fast. You see the maximum PRF, the maximum trigger rate, is higher for one channel than two, because with two channels, although the acquisition is simultaneous on both channels, you have to download twice as much data, because you have to download the two channels instead of just one. So as a result, you can't keep up with the trigger rate that you can in single channel mode. So that's these two data here, these two data sets here. We've modeled the behavior of this PRF curve, as we call it, and I argue we've pretty much perfectly reproduced the behavior, I would say. And the way you model it is to say, well, in order to acquire the inverse of the maximum PRF, which is the spacing between two triggers, has to exceed all the things I have to do in order to handle a waveform. Well, first thing, I have to acquire the waveform. There's no way around that. And then I'm in single record again, so I'm not stacking the waveforms. I have to transfer the data. So I have to count the transfer time through the PCI Express bus. And then finally, there's this overhead time, which is really all the constant things that I have to do with every acquisition. So one of those things is to rearm the card's trigger circuitry. But in addition, I have to set up the PCI transfer, maybe stop the PCI transfer, and I sweep all these little constant things together into this sort of dustbin overhead time I have. I've shown the two equations up here that fit these two dashed and dotted equations to the data, and we can see here that both of them contain in gray this second term. The acquisition time is the same, and that's pretty straightforward. That's the depth, the number of points I'm going to acquire, divided by the sampling rate. In this case, the sampling rate was different. in the single and the dual channel mode. But otherwise, the equation is the same, and that's pretty straightforward. The transfer time is a little bit more difficult. It's also proportional to the depth. Okay, we take the number, but we have to multiply by the number of channels now, because however many channels we download, we have to multiply. So we have to multiply by 2 in the dual channel case, the dashed line, and then we have to multiply by, we have to turn the number of samples into a number of bytes. Okay, and this is a 12-bit card, but we actually the samples for the card actually occupy 16 bits. Okay, so there's 2 bytes per sample coming from this card. So we have to multiply by 2 in order to get this numerator in this red term here in, oops, sorry about that, in bytes, okay? And then we divide by a transfer rate, a data transfer rate, which I just plugged in values until it fits the curve. I got 3,800 megabytes per second, almost 4 gigabytes per second of transfer rate. And finally, there's this overhead time, okay, which is slightly different for 1 and 2 channel acquisition. You can understand how you might have to do more things in order to set up. You have to set up 2 PCI transfers, for example. PCI Express transfers in the case of dual channel mode. So the overhead time is, sorry, I keep pressing shift instead of control, is slightly bigger in dual channel mode than in single. So this equation kind of neatly divides these curves into 2 domains. Notice they're on log-log plots. When the depth is very small, when you're acquiring only a very small number of points, like 1,000, for example, if you go from 1,000 to 2,000 points, you can still attain only about the maximum pulse repeat rate, which is about 10,000 waveforms per second. And that's because basically the overhead time, the fixed things that you have to do add up to more time than it takes to acquire the waveform. So whether you acquire 1,000 or 2,000 points doesn't really matter. You're in this overhead time dominated region of the curve, and basically you're topped out at 10,000 waveforms per second in single channel mode. If I go to the other end, the other limiting domain at very high depths, well then the overhead time starts to become insignificant, and we're dominated by the transfer time. So we're limited, that is to say, by the transfer time. So if we go from acquiring a 10 million point to a 20 million point waveform, basically we can only do that at half the repetition rate, because there's twice as much data. It takes twice as long because you got the waveforms are twice as big. There's twice as much waveform to download. It takes twice as long, so you can only trigger the card at half the rate. So this, as I say, tells us how we really understand how our memory mode of operation works. We described it for single record mode. It's a little tricky, a little more complex for multiple record, but not too much. Really shows that we understand how the product works and how the transfer time trade-offs work. And so a customer will come to us and say, look, I've got 10,000 point waveforms and they're coming at a 1 kilohertz trigger rate. We can quite happily say, well, you're right here. You're right here on this graph, and you're a good factor of 10 away from the limiting case. So really, it's as easy as pie for us to do a 1,000 hertz repetition rate with a 10,000 point waveform. Okay, so we use this in our application engineering of customer applications to ensure them that they can keep up with the trigger rate that they have. So let's move on to streaming mode acquisition. Well, streaming is very simply the ability to dump the waveform data directly onto the PCI bus, much as Netflix, dumps the movie onto the Ethernet. But and that can be sent to various streaming targets. One of our most popular ones, let's say, is hard drive. If you just want to store the data and you can stream the data to hard drive, well, then you've increased your 1 or 2 or 5 gigabytes of onboard gauge memory to terabytes or tens of terabytes, even hundreds of terabytes. So we can increase our memory storage by a factor of 10,000 by streaming to hard drive. So that's a very popular choice, and indeed we sell complete turnkey stream to disk systems that work, we call them recording systems. They just record for hours or even days because of this huge amount of storage. Alternately, you could stream the data to some sort of processing engine that might apply some DSP, some digital signal processing, to the data and hopefully reduce it somewhat. That processing could be in the CPU, so you could have the CPU perform calculations on the waveforms, or increasingly starting to use GPU cards, right? So there's these graphical processing unit cards available for the video game industry, and they're ideal for processing waveforms. Other possible PCI targets could be a waveform display, or you could imagine streaming the data out the Ethernet to some other repository or analyzer, if you will. And in all cases, if you were going to do this, the consumer would have to be able to keep up with the stream. Otherwise, there would be an overflow, which would result in data loss. That's the general idea of streaming. So to recap a bit, we said how, or if I didn't highlight, in memory mode, the memory is only doing one thing. You're either acquiring into the memory or you're transferring the data from the memory to the PCI bus. You can only do one of those two things. Whereas in streaming, we can acquire and transfer from the card's onboard memory simultaneously. And in fact, we use the onboard memory as a FIFO, that's a first in, first out buffer, to absorb small PCI Express latencies, as I'll explain in more detail. And the memory gives us a kind of a data loss alarm. If a PCI bus latency is long enough that this FIFO memory overflows, we can get an alarm that'll tell us, hey, we've lost data. Conversely, if we never receive this FIFO overflow alarm during a streaming acquisition, we can be sure that we haven't missed one drop of data. Just as in memory mode, streaming acquisition can be in one shot, or single record mode, where we just give one trigger to the digitizer and then have it digitize continuously for minutes, hours, or even days. Or alternately, we can work in segmented mode, the streaming analog of multiple record, where we send multiple triggers to the card, and it acquires in a sort of a machine gun fashion, very quickly dumping repetitive waveforms with gaps in between. But they're very similar in many ways, right? In both cases, you've got this continuous, either unbroken or segmented stream of data that you've got to, or the consumer has to consume quickly enough. So the great promise then of streaming, and reality of streaming, is we can achieve 0% data loss, which is unachievable in principle in memory mode. Here's an image of a more detailed image of how streaming works, how the memory works. But basically, the brains of our card is an FPGA. That's a field programmable gate array. We don't use processors of any kind, because the FPGA is more like configurable circuitry, okay, and we really need that sort of device in order to handle the huge throughput that we have. For slower devices, you can get away with the sort of higher level processor and move data around in a more computer programming sort of fashion. But here we need the ability to send the data through the equivalent of high-speed digital circuitry. So indeed, the stream is created by the ADC, the analog to digital converter chip on the digitizer card. The stream goes through the FPGA and into the card's onboard DDR memory. And then at the same, so this memory is dual ported, okay? Meaning you can write to it and read from it at the same time, which doesn't occur in memory mode. In memory mode, you're only doing one or the other. At the same time, we're emptying this memory asynchronously with our streaming software, which is transferring the data ultimately in blocks from the onboard memory. So the onboard memory is an asynchronous FIFO. We mean by asynchronous that the filling and the emptying are unrelated. And in fact, in a one-shot application, the stream rate into the memory is continuous and constant, whereas you might be emptying it in a fits and starts fashion, which is fine. And as I say, if the PCI bus or the process of doing the transfer was locked up for any reason, and this point was choked up, the FPGA memory, sorry, the FIFO memory, the onboard memory, would start to fill up. Okay, just as if you had a slow stream going into a sink and you plugged the sink up, the level of the sink would start to rise. But as long as you pulled the plug before the sink or the FIFO memory overflowed, you wouldn't miss any data. So as I say, this FIFO is mostly empty, but if there's any sort of blockage for whatever reason on the PCI bus, it'll fill up. Since we have a second or two or five's worth of memory on the card, that means we can absorb latencies as long as several seconds, which basically never occur. So, so a normal application, normal operation, as long as the consumer can keep up, and as long as the ADC isn't overtaxing the PCI bus, there should be no reason for data loss. But again, if there were for some reason data loss, you'd know about it because we would issue this FIFO overflow flag. So that was I should have said, the hardware and firmware architecture, streaming architecture on our Gauge CompuScope digitizers. How does the software work? Well, in order to understand that, you have to understand that there's in a multitasking modern OS like Windows or Linux for that matter, there's two levels. There's the application level, where applications like our GaugeScope software and Word and every other application that we use under Windows resides. And then below, at a lower level, there's this kernel level, okay, which has to do with which is where the card is, our cards are actually programmed at a very low registry level, okay, where data are moved around. You can access physical memory at this kernel level. So in a way, all the real hardcore heavy lifting is done at the kernel level. And yeah, I mean, very much for our card. So people sometimes call and they say, hey, do you have a register level programming map for the Gauge card? You say, no, you're remembering back to the 90s, sir. Nowadays, all that is done by our drivers at the kernel level, and then we present a nice, easy to use software API that you can access from your application level application, okay, and it sort of covers up all the difficult bits in the kernel. Well, similarly, we the large part of the sophisticated streaming operations going on at the kernel level, and we communicate with applications at the application level through these two toggling buffers. Okay, we have a pair of buffers that sit at the boundary between the application and the kernel level, and these buffers are special. When you allocate a buffer at the application level, that buffer can be fragmented. It can exist all over the memory in little bits. In fact, it even reside on the hard drive. It's a process called thrashing. The Windows operating system will sometimes decide to use a bit of fast hard drive for memory. And when you allocate this buffer, it can actually change over time. So these little fragments are moving around in memory space. Now that doesn't wash for streaming. The card needs a very well-defined buffer into which to stream as a target. So the memory into which our card streams has to be physical and contiguous, okay? It has to be one piece of what we say locked down memory that doesn't change over time and is all in one contiguous block, okay? So we found that you can allocate something like up to about 100 megabytes. Even that's pushing it. It'll depend on how much RAM you have in your PC and other factors, how many processes are running. It'll actually go down over time. So basically these buffers are limited to a few megabytes. How do we use these buffers? Well, we toggle them, okay? We stream, the card streams the data into one of the buffers while the other one is being emptied by the target, okay? So the analogy I always use is you're at the bar and the bartender is pouring out a bottle of scotch and you have 2 shot glasses and you're having one filled as you drink the other, and then you swap and you drink from the full one and put the empty one down. And as long as you can keep drinking fast enough, there'll be no spillage. And this analogy really works well for the streaming. As long as the consumer target can keep up with the data rate, there'll be no data overflow. If the consumer isn't fast enough, in fact, the stream will kind of back up and you'll always get a FIFO overflow from the memory on the card, which is actually down here. So that's, as I say, the mechanism we use to interface the data stream to the customer's application, these specialized dual toggling RAM buffers. Okay, as for what the target is, that can be 3 main things, I would say. The very popular disk target, which, as we said, expands the storage capacity of the system well beyond the memory on the card. Then we have analysis. You might want to analyze and reduce the data. You might be looking for some signature. We had a customer looking for a certain type of military aircraft. He just watched the data came in and ignored it until he saw the signature, radar signature from that plane, and then he sounded some sort of alarm or whatever it is. That's an example of streaming to analysis. You might want to stream to an FFT process, some sort of peak detection process. There's any number of different sorts of analysis or DSP processes you can imagine. Finally, a target is application level RAM. So we said you can only allocate about 100 megabytes of these toggling RAM buffers, but at the application level nowadays, you can allocate, terabytes worth of buffers. So we have a customer whose entire streaming scan takes about 100, creates about 100 gigabytes of data, and he streams through these toggling buffers to a big, huge application level RAM buffer, and then he can go through. He can look through the buffer, this 100 gigabyte buffer, and get rid of the stuff he doesn't need and crop the data, basically, right? So he can duplicate the raw signal into PC RAM. So those are the 3 potential targets. Just a word about streaming limitations. Streaming is a more sophisticated way of operating the card than memory mode, and so it takes a little more investment and know-how, let's say, by the customer. First of all, our standalone gauge scope software, or flagship oscilloscope software, gauge scope, does not support streaming. We do have another software called DS Scope that does support streaming to disk. We've got customers who can set themselves up stream to disk systems quite easily using that software. We don't support streaming under LabVIEW or MATLAB. These are protected high-level languages, multi-buffered environments. Our angle is we really don't see why you would want to bring a data stream into LabVIEW or MATLAB. We're toying with maybe creating a sort of an empty shell application where you might launch a streaming application from LabVIEW, or MATLAB, but actually bring the data in so that you could then use the inefficient calculation tools. I mean, they might be very sophisticated, but they're not particularly performant. So really, if you want to stream and you want to program the streaming, you really should work in the C environment, and that's what we support. Finally, we've already alluded to this limitation. The customer, the user, is responsible for ensuring that the target is able to consume the stream. We usually say we can do our part of the job. We can get the data to the PCI bus at these incredibly high rates, like 4 or 5 gigabytes per second. The PCI bus is able to do its job and translate the data, transmit the data along at these high speeds. But if the consumer chokes on the data and isn't able to consume the fire hose, let's say, of data that's coming at them, then that'll cause a block up and lead to a FIFO overflow and lost data. Okay. We provide in our C software development kit three main streaming examples that can serve as a starting point for the customer's application, or the first one anyway can be used as is to stream to very large amounts of disk memory. The second one, as I say, is streamed to analysis. The second target, we do a simple summing analysis in the CPU that the customer can replace with his or her own CPU processing algorithms. And finally, as I say, we have an application that streams to PC RAM, more specifically application RAM, where they can allocate huge buffers and then operate on data in the PC after acquisition. A word about streaming and PCI generation. So the PCI Express bus, our CompuScopes are on the PCI Express bus, and they use the 8-lane or X8 version of the bus, which is sort of grown to become the de facto instrument card standard. And we've got cards in 3 generations currently. We've got Gen 1 cards, actually some of our Signatech cards. The specifications on the Gen 1 PCI Express bus tells us that the theoretical maximum rate is about 2 gigabytes per second. We found, however, that on our Gen 1 Signatech digitizer cards, we can sustain about 1.7 gigabytes per second. And the rate is lowered because of things like handshaking and so forth. The theoretical rate is sort of a best case rate that you can attain for very short periods, for very short bursts. But in our case, we're typically streaming huge amounts of data, terabytes of data. So we need more an average measured sustained rate, as I say, is 1.7 we found for Gen 1. For Gen 2, some of our older generation gauge cards are on the Gen 2 bus, which goes at a theoretical maximum of 4 gigabytes per second. And we found we can attain somewhere between 2 and 3 gigabytes per second. Finally, our latest cards on the Gen 3 bus with a theoretical rate of 8 gigabytes per second, we found we can sustain rates of up to 6 gigabytes per second. The 2 new generations, 4 and 5, I believe Gen 4 was delayed by several years, much so that it looks like most people are kind of leapfrogging Gen 4 into Gen 5. Gen 5 slots are starting to appear on the market, so that's sort of the future of the PCI Express bus. A word just about some of our cards and their ability to stream. If we look at our older Gen 2 cards, our 3 main families, Octopus, Razor, and Cobra Max. If we take the sampling rate, maximum sampling rate of these cards, multiply by the number of channels on the card and the number of bytes per sample, which is usually 2, but is 1 in the case of our Cobra Max cards because those are 8-bit cards, then we get the maximum stream rate that we can expect from the card. And we find in 3 out of 4 cases for our older Gen 2 cards that we're able to keep up, whereas our fastest card, the Cobra Max card, is able to generate data faster than the Gen 2 PCI bus can handle, and that's okay. I mean, we design our card with a dedicated bus going to the onboard memory, and there's no way that a shared bus of any kind is ever going to be as fast as you can design on a tight dedicated bus on a card. So there will always be cases where the card can go faster than the PCI bus. Indeed, if we go to our newer generation of cards, it's a newer generation of PCI Express, so it goes, in fact, about 3 times faster. But our cards digitize at such faster rates that we've actually got less cards that can stream at full rate. So if we look at our Eon card, it can actually create data at twice the rate of the PCI bus, which is, again, okay. You can either back off the sampling rate if you want to stream continuously, or if you're taking short waveforms, you can take waveforms only 50% of the time, and then you will be creating an aggregate data rate that is within the speed limits of the Gen 3 PCI Express bus. Our Razor Max card, our 2-channel card, is well, let's say it the other way. Our 4-channel card could create enough data to exceed the PCI bus, but at half the rate, our 2-channel card is all its data rates are within the speed limit of the PCI bus. So the 2-channel Razor Max, the PCI bus can take everything that the card can throw at it. Just a word about the asterisks here. we said that most of the time we use 2 bytes per sample on our Eon card. Since it's a 12-bit card, 12 bits is actually a byte and a half. So we're actually able to use on the Eon card a packing mode where we really pack the data in as tightly as possible, and we only use 1.5 bytes per sample instead of 2. We're even able to throw away the lowest 4 bits if the customer is more interested in speed over resolution to get that number down to 1. So this way we can fully exploit the speed of the PCI Express Gen 3 bus on that card. This slide addresses a concern that we sometimes get from customers, okay? So the concern is, hey, the way you guys do streaming is you stream through PC RAM. What the customer says they want, I really want PC direct streaming, okay? The ability to stream the data directly, say, to the hard drive rather than going through PC RAM, the way I've just described a few slides ago. And why is there concern about that? Well, if we go back to the days of the PCI bus circa 2000, okay, the original PCI bus could run at rates of about 100 megabytes per second sustained. And if we go, and in those days, the architecture of motherboards was typically such that everything was a PCI bus, was a PCI device, I'm sorry, including PC RAM. Now, I probably should have drawn some wires in between here, but the point I'm trying to make here is that by going through, by doing a RAM-mediated streaming transfer, you're actually going into the RAM and out. And if this data throughput rate is limited to 100 megabytes per second, you've actually created two-way traffic here, in and out. So that means you can only have 50 in, 50 out. So by doing RAM-mediated transfer, the customer argues, I'm actually going to cut my maximum rate down to half. Can't you give me a direct streaming to the device? And indeed, we could do that way back in the DOS old days, the days of DOS, where we were able to tell the card, look, go to this memory location, this physical memory location that corresponds to the hard drive. And indeed, we were able to stream directly and address the customer's concern. That sort of direct access has become, I would say, practically impossible under Windows because of the way Windows abstracts the memory and does not use real physical memory addresses, you know, D000, like we used to back in the 90s and before. So that's the bad news. The good news is the motherboard architectures have improved to the extent that the two-way traffic concern is no longer really a concern. So if we fast forward 22 years to the PCI bus running now at 6,000 megabytes per second in 2022, we can see, first of all, the slots aren't shared. We can have dedicated, okay, because of the serial nature of the PCI Express bus, we can actually have dedicated bus lanes that don't have to share data. That's number one. Number two, the CPU's memory bus, it now has a dedicated memory bus. It doesn't use the PCI bus like everybody else. It's got these dedicated bus so much, it's become so integrated that my understanding, it doesn't even really have a name anymore. It used to be called the front side bus, but it runs at rates of 200 gigabytes per second, and we're looking at the next generation being something like 1200 gigabytes per second. So this enormous rate means that the two-way traffic is no longer a concern. Yes, there still is two-way traffic when you do a streaming transfer mediated through RAM, but since there's so many lanes, to use the car traffic analogy, it's really no concern. It doesn't bottleneck anything. So the happy conclusion is that we no longer have to worry about going through RAM. It doesn't really affect us at all. And we have the great advantage now that we can access the stream on its way if we want to. Here's a picture of one of our most powerful stream-to-disk systems. This is nowadays using modern SSD solid-state drives that are much faster. Here we've got a system consisting of 8 terabyte drives, 24 of them for a grand total of 192, almost 200 terabytes of storage. As I say, it uses a RAID system where you kind of use multiple slower disks in parallel, okay, to effectively add up the throughput, right? So by dealing out the data like cards, the rate going into any individual hard drive is relatively slow, and you can multiply up the speed of the drive by putting them in parallel. So as I say, by having this number of drives, we've been able to achieve 192 terabytes of storage. That corresponds to at least a day, if not days, of storage, depending on what card we're talking about. And we can make the speed of these drives, 12 gigabytes per second or more. So more than we need for our maximum 6 gigabyte per second that the PCI Express bus can serve up. So we can actually make drive systems that will not be bottlenecks and will not choke on the data, leading to data loss. So as I say, we put a card in a system like this, and we can deliver you a complete turnkey system that acquire for days at a time in an unbroken fashion. Another target we can use is a GPU, a graphical processing unit, that exists on today's graphical processing cards used by the video game industry and they're vector processing. So typically they're processing vectors used for character positions and so forth. And of course, a waveform is just a vector by another name. So really, GPU is an ideal candidate for processing waveforms coming from a gauge card. So we can stream data from our gauge card to the NVIDIA GPU card. We use the easy to use NVIDIA CUDA C library to manage the card, and the customer can put his processing into the card, process the data, hopefully reduce it a bit before sending it on, say, to a hard drive. So the width of this stream might be less because of some data reduction that may have gone on in the processing. The user might be picking out only, the odd peak out of a huge data stream, thereby reducing the data by factors of thousands or even millions. Here's an example of a benchmark we performed using a GPU card, and I won't get into too much detail here. We programmed it to continuously perform FFTs on the data stream, and we find that when the FFTs become long enough, the processing rate by the GPU card beats the processing rate by the CPU. If you've only got relatively short FFTs, it turns out you spend more time moving the data around. So the GPU card, being remote from the processing unit, slows it down. Basically, you've got to get the data over to the GPU, even if it's more powerful. That trip costs you more than what you would save by outsourcing the processing from the CPU to the GPU. But once the FFT size gets beyond about 10 or 20,000 points, well, then the overhead, the loss of the transfer starts to pale into insignificance, and we can process FFTs more quickly on the GPU card. So we're starting to add more examples to our GPU kit that we sell, so that customers can get up and started with their own GPU, stream to GPU applications as easily as possible. Finally, to complete the streaming story, Gauge has had for many years now the ability to perform custom digital signal processing on board our FPGA. So for most customers, let's say we focus on getting the best, highest fidelity data to the customer's application in as quickly as possible and in as easy to manage a fashion as possible. But since we've got some empty space in our FPGA, we started putting processing into the FPGA. And if we combine that with streaming, then we can really look at, creating a data stream, processing it, hopefully reducing it as well, so that we can reduce the data rate, thereby offloading the processing from the host CPU, but also reducing the data rate so that other processes don't choke on it. We can put our expert processing typically for the processing elements that we have that work in memory mode. we do it before memory, and that has the advantage of increasing the effective size of the memory. If the expert digital signal processing DSP reduces the data, say, by a factor of 1,000, then you've proportionally increased the size of your memory by 1,000. We found, however, in streaming, it's better to put the processing after the memory. That way, you can download the raw data and compare it to your processing and make sure that you're doing the processing in the right way. So these are the two potential onboard processing architectures that we support. And as I say, the second one is more appropriate for streaming. If we put not all the acquisition elements that we have together, I'll introduce a new one here, which is down converters. So what I have on the right side here is a stream to disk system. Here's a signal coming in. It goes through the ADC, through the FIFO memory, managed by the FPGA. The data are put on the PCI bus, streamed to a RAID array so that we can have a recording system that can record several hours or days even of data. But what we then do is we put what's called a down converter before our digitizer. What a down converter does is it can take in actually airwaves at very high carrier frequencies. So these, in my example here, I've got the RF waveforms coming through the air with frequency ranges between, in this case, 22 and 24 gigahertz. Now that's a 2 gigahertz bandwidth, okay, but offsetted so that it sits around a center frequency of 21 gigahertz. What the down converter does is it shifts down, as the name suggests, that central frequency, in this case from 21 gigahertz way down to 1 gigahertz. So now the signal frequency doesn't range. It still has the same bandwidth of 2 gigahertz, but instead of spanning from 22 to 24, it goes from 0 to 2. So basically, we've shifted this super ultra high frequency signal down with a bandwidth that we can handle down to a lower frequency that we can handle. I sometimes use the analogy of a ladder, right? If I'm a 6-foot man, I can work in a 6-foot area. But if I have a 100-foot ladder, I can work between 100 and 106 feet. I still only have that same 6-foot working range, but with the ladder, I can offset it. And that's sort of what the down converter does. Now, if we combine really, I'll add yet another element, which is our waveform generator. We actually have a Signatech waveform generator, which is the exact opposite of a digitizer, to which we can stream data. So this allows us to create a record and playback system, right? So if I ignore the blue external blue boxes for the moment, we can take in a waveform, record it for hours and hours, and then play it back in exactly the same fashion, except in reverse, okay? And here I've actually added an element of streaming through a DSP block. And in fact, I'm using DDC, which is digital down conversion, which is the digital analog of these analog down converters. So there's kind of a two-step, in this case, a down conversion process. So now we add a down converter on the digitizer side and an up converter on the generator side, which is the exact opposite of a down converter. And now we have the airwaves coming in, get down converted, get digitized, down converted digitally again, streamed to disk. And then at any time later, we can replay those same signals and basically do the same thing in reverse, stream the data from the disks through the digital up converter, out and through the analog up converter and turn it back into RF waves. We had sold a system like this to a customer who was setting up a local military positioning system. In the military, you got to be prepared that your GPS, your satellites might be taken out. So in doing this, they listened to the satellites, and the great success of our RF record and playback system was we were able to record the actual signals from real satellites and then play them back. And we actually tricked the GPS device into thinking that these were that this was real satellites, and it calculated its position on that basis. So that was sort of a win. So as I say, this has everything that we have together in one system. Okay, so now I'm going to talk about data throughput versus data latency. Okay, advance please. Okay, so you might Data throughput is the rate at which the data is transferred through a certain interface, let's say. Data latency is how fresh those data are. And you might expect that those two things would improve together, and indeed they do to some extent. As your raw transfer rate improves, both the data latency and the data throughput improve. However, you can optimize the improvement of one as compared to the other, as we'll see in a minute. Now, historically, Gauge, we've focused on high data throughput. Most of our applications historically have been post-processing applications. The customer acquires a certain amount of data, large or small. They might do a huge scan. They transfer all the data into the PC, and then they slice and dice it into making images, basically at their leisure, with no pressure. That's a non-real-time post-processing application. And in those applications, you really don't care about data latency. If the data comes through a little late by a few milliseconds or seconds even, you're okay as long as you end up with everything and can process it within reason. So latency isn't important in a post-processing application. However, in a real-time application, latency is very important. Two great examples of this are control systems, where you actually have to take the data from some sort of system and then provide some sort of feedback to control the system. And if you're unable to do that, if your data that you're using to control are not fresh, then you're kind of closing the barn door after the horse has already left the barn, sort of thing. Another obvious real-time application is electronic warfare. You're in an airplane and you've got an enemy missile aiming at you, and you're listening to its signals, and you're trying to output countermeasures. You need to have the very latest and greatest signals. If you're working on data of where the missile was 10 milliseconds ago, you're Johnny-come-lately, and you might just be blown out of the sky. So there's an application where data latency is very, very important. And we're increasingly starting to get into real-time applications. So I wanted to discuss this issue. Next, please, Susie.
Okay.
So this slide basically shows that all latencies associated with our card are typically measured in nanoseconds. Onboard clocks typically have periods of nanoseconds. Operations associated with our card take tens or hundreds of clocks. So basically, the latency as the signal ripples through our card only amounts to some number of nanoseconds. By contrast, the buffers that we talked about, the dual toggling buffers that we use to transfer the data to PC RAM, those typically hold data that corresponds to milliseconds worth of data. And if you think about it, if you're filling this buffer and then transferring it, the first points that you fill in the buffer become old. So if the buffer is containing data that corresponds to 10 milliseconds worth of data, let's say, then the oldest data in there, that's the transfer rate, not the sampling rate, the oldest data in there are 10 milliseconds old. So it turns out that these transfer buffers are the key that determines how much latency, and indeed what the latency throughput trade-off, how that works, as we'll see on the next slide. So on the next slide, we've looked at different buffer sizes, and indeed the customer can adjust these buffer sizes in order to optimize them for his application. Here I've got a number of buffer sizes ranging from only a kilobyte way up to 10 megabytes. We said that the maximum achievable is something like 100 megabytes, so that's reasonable. And then we've assumed a 1 gigabyte per second stream rate, and then the filling time, the time to fill a one kilobyte buffer is 1 microsecond. So that means that's also the worst case latency. If it takes a microsecond to fill a buffer, then the oldest data in that buffer are 1 microsecond old. Okay, as you raise the buffer size, that latency goes up to, in the extreme at 10 megabyte buffer size, the oldest data in there are actually 10 milliseconds old, 10,000 times longer. So that would say, hey, we want to keep the buffer as short as possible so we get the very best latency. But, there's a trade-off. So in order to illustrate the trade-off, I've chosen a reasonable number. This isn't a measured number, it's an estimated number, is the amount of setup time you need to set up one of these buffers. So it's not just the amount of time it takes to transfer the data that we got to think of. We've also got to think of the amount of time to set up that buffer. And I've picked 10 microseconds as a reasonable estimate for that setup time. If you use a 10 megabyte buffer in the extreme here, then that buffer takes 10 milliseconds to fill. So what's another 10 microseconds? That only brings down your effective throughput by 1 part in 1,000. So instead of transferring at 1 gigabyte per second, you're only transferring at 0.99 gigabytes per second. So by using a very big buffer, we've gotten bad latency, or the worst case latency at 10 milliseconds, but we've got very good throughput. If I go to the other extreme, where our very short buffers that only take a microsecond to load, well then the total loading time is actually 11 microseconds, because you've got to set up that transfer for 10 microseconds. So that brings down your throughput by a factor of about 10. Instead of transferring at about a gigabyte per second, you're only transferring about 0.1, a little less than 0.1 gigabytes per second. So that's the downside to using short buffers, is that any setup time required to do that transfer is now proportionately more important. So again, just to summarize, short buffers are good for good latency, very fresh data, but it gums up your transfer because you're spending all the time going back and forth, back and forth. On the other end of the spectrum, use very big buffers. That gives you very bad latency because the first data that get loaded into that buffer are old by the time the last data are loaded. But the upside is by filling, now you're spending less and less time going back and forth to the well, if you will, and you can get the very best throughput, almost the full transfer rate of 1 gigabyte per second. Next, please, Susie. So in grand conclusion here, we've introduced streaming mode, and this is really, although the operation is a little bit more sophisticated than memory mode, it gives you the very best throughput you can possibly use, and most of our customers doing high throughput scanning applications and so forth are taking advantage of our streaming functionality, which allows you very generally to offload the data and acquire the data at the same time, instead of doing it at different times as in memory mode. We talked about the different streaming targets we have, a RAID drive array that can be used for straight recording. We sell recording systems with no software programming required. For programmers who want to work their own application, we can do analysis in the CPU or GPU. We mentioned also we can do onboard processing in our firmware. And finally, we can transfer the data to a large application RAM buffer where you can stockpile it for long periods of time. We talked about using other instruments such as our Signatech PXDAC 4800 streaming generator that works just like a digitizer in reverse. You can stream data to it, blast data out the back of it, and we can put these together, a digitizer and a generator together, to make a record and playback system that I say works very much like an old tape recorder, where you can record and listen to it back, but at, of course, thousands of times, or thousands of times the speed of the tape recorder. We can add bookended up and down converters so that we can shift our waveforms from ultra high dozens of gigahertz carrier frequencies down to baseband, lower frequency as we call it, so that you can imagine pulling in a waveform, an air wave, processing it and blasting out again. You could spoof a missile this way, for example, right? The missile's coming in, listening to your radar, or it's bouncing radar off you. You could listen, capture those radar signals, and then generate false radar signals that say, I'm over there, don't hit me, for example. We talked about real-time systems where you need to know the answer. You need to process and get the answer, make decisions as the waveform's coming in. And we talked about latency versus throughput in these issues. So for the final slide, I'll just present some of the applications we've been involved in. One big one we've been, as long as we've been able to stream, involved in is signal intelligence. These are people who want to listen into, I won't mince words, spies, right? Agents who want to listen into what other people are saying or doing, and we can create a streaming system that can listen to high-speed signals for 24 hours or more. You can't do much with a few milliseconds worth of data in the onboard memory, but if you pair it with these very long hard drive capacities, we can store for very long human intervals of time. Lightning monitoring is a big streaming application for us. These lightning monitors need to get the latest lightning signals off of their detectors and stream it, because the lightning can come continuously. They do segmented streaming because lightning hits in bursts, so we use the segmented streaming mode for that. We discussed the GPS monitoring application, where we were actually able to trick the GPS device into believing that our system was actually, the satellites up in the atmosphere, up above the atmosphere, actually in orbit, sending out their signals, which is pretty cool. We've got a radar application where a customer is streaming to GPUs and making calculating continuous FFTs, much as we showed in our GPU example. I alluded to a scanning application. It's actually an ultrasonic scanning application where the customer scans, creates 100 gigabytes of data, which he uses our variation on our stream to RAM application to reproduce or accumulate this data in PC RAM, and then you can look through it and crop it and store the interesting bits. We've been involved in a cryptographic applications where we stream through this DDC firmware that we discussed. Again, the digital analog of the analog down converter that allows you to shift waveforms to lower frequencies and thereby reduce the effective stream rate. So by having this DDC firmware, the customer was able to dramatically reduce the amount of data that he acquires over several hours. Finally, we work with a company that makes threat emulation systems. These are systems that simulate the theater of war and all the various radar and communication signals. And we provide record and playback systems that interact with this threat emulation system and make sure that it's doing what it's supposed to. So those are, I guess, 7 applications we have, real-world applications where people use streaming to get the best out of their application. So that ends the presentation. I'll hand it back to you.